start on the next one a little bit. So that's what I was planning on doing. Excuse me. Should I get something? Okay, we kind of ended, we were talking, I know we got to the next one, but I wanted to just remind you what we were talking about with the depth and what we can do with it, because by then it was at the very end of the class, and kind of figured that needed to come back and re-go over this a little bit. Remember that we can do broadband decoupled, and what's broadband decoupled? Regular C13 NMR, okay? And that gives us everything, hopefully. And then we go and we can do a depth 90, and that's going to give us only the CHs, and the depth 135. That's going to tell us the CH3s, because we can subtract off the CHs, and the CH2s, because one will be positive, one will be negative. Okay, so this is what we're dealing with. So this, notice that the quaternaries are nowhere in either of these. So if it's here and it's not in any of these, it's a quaternary. If the CH is here, then we can subtract it out and know that the others are the CH3s. CH2s are negative, and so as you can see, we can figure out at least whether they're a quaternary, primary, secondary, or tertiary type of a carbon environment. And that can be very, very valuable. Okay, so let's go back and re-look at this one again, and just see what it looks like when we're doing this. Okay, so here we have the broadband decoupled. And when we're doing that, we see 1, 2, 3, 4, 5, 6, 7, 8 carbon environments. Am I counting those correctly? I can't really see those very well. Anyone else getting something other than 8? Everyone getting 8? Okay. So here we have, when we're looking at these, we automatically know that this region is probably going to be what? It's going to be the double bond region. So we know that when we're looking at it, these two are in here. Now, the thing that we see is the depth 90 only has this, and the depth 135 only has this. That means this one must be what? Quaternary. Okay, everyone following along? It must be quaternary. We got it? Okay. So now, which of these two carbons would fall as one that doesn't have any hydrogens on it? The one on the right or the left? Carbon has 4 bonds. So which one doesn't show any hydrogens on there?
The one on the left.
Yeah, good job. The one on the left. Okay, so that means this one has to be this one here, and this one then would have to be this one. Okay, everyone kind of see how we're doing that? All right, so we got that one out of the way. Okay, now we have a depth 90, which is a CH. When we're looking at a CH, where do we have a CH in there? Plus, look at where it's located. What does that tell us it's next to? The oxygen, yeah, the electronegative oxygen. Okay, so that means that this one here must be which one? Because it is also located here. So which one is that one going to be?
One on the far right. Yeah.
Right there? Okay, so now we've got those. So we've got those 3 figured out, okay? All right, we're moving along. All right, now we've got some CH2s here, and we see that there's 2 of them down here. And we have some CH3s as well. We see that there's 3 CH3s, and that's exactly what we would expect is 3 CH3s and 2 CH2s here. So at this point, we've done pretty well. Now the question is which of these 2 is this one here? Well, it's probably the one that's bonded to the carbon with the OH, okay? But it might not. I mean, we have a double bond here as well, but I would think that that would be a good possibility. And then on these 3 CH3s, let's think about that one just a little bit. What's going to matter? Well, this is bonded, if this one's probably shifted, this one probably is too, right? And so it's probably one of these on up here, not this one way down here. So even though we now see how many CH3s we have and how many CH2s, taking it from that can be still a little tricky. We at least see and get it. So this is, again, I'm gonna put a plug in for the ChemDraw. This is where you can go in and see, hey, what does it look like when you're doing all the math on it for us? And as expected, this 2360 is going to be the second one over that's the CH3, and the 38.9 is the one that is the CH2 that is the more deshielded one. The 23.2 is the one that's next to the double bond as far as those two go. So when we're coming back and we're looking at this one would be the one that's next to the double bond, and this would be the one that's next to the O, it's with the OH. Okay, so this one would be this one here, and this one would be this one here. Okay? Now let's look also then at these methyl groups. And again, this is just a really good tool that helps you figure these things out a little bit better. And when we do that, we can see that we have a 23.6 and a 24.6. So what that means is that this one's the furthest one, and then this one, and then this one, when we're looking at it. So, like we said, there are a lot of things we can do with it, but I forgot to bring this up, so hold on a second. But the ChemDraw, it does the math. Is it always right? No. But on something like this, it can really help us figure it all out. And there's other things that help out on this, such as when you look at the proton. I mean, you're going to have some other things to help you figure out. It's not just going to be one of them. Getting there. So this is our work example. And what's the first thing we're going to do? We got C4H10O. What's the very first thing we do?
Degrees of saturation.
Are there any?
No.
No, there's not any degrees of unsaturation, are there? 2 times 4 is 8, plus 2 is 10. We ignore our oxygens, so we have 10 hydrogens, and it all works out. Okay, then we have a broadband decoupled, and we've got 3 carbon environments. And our depth 90, what is the depth 90 telling us? CH, so we have 1 CH, and then this is not given here. This one should be in here, and they didn't put it in there, but they should have, because it's a depth 90, it should be in the depth 135 as well. I guess they were just saying, well, this is where we're gonna find that or something, I'm not sure. I think it was probably a misprint, but anyway. And then the 135, we have the 19, what is that? 3, and the 69.5 would be a CH2. Okay, so through all of this, we have what? We said that we have 1 CH3, our environment, 1 CH2 environment, 1 CH environment. Okay, so we've done all of that, and have we taken into account every single one of our peaks? Well, we have, haven't we? Okay, so in other words, do we have any quaternaries? Are there any quaternaries? Anybody? there's not. Thank you, Ned. I appreciate that. There's none because we're only showing 3 on the proton, on the broadband decoupled, and we are showing 1 here, 1 here, and 1 here. So we've got them all accounted for. Okay, now it's saying it's an alcohol, so we know we have an OH, right? Everyone remembers OH is alcohol, right? Okay. And what kind of carbon is that going to be bonded to? Which one is that going to be? Where would an OH be? Would it be at 19, 31, or 69? The carbon that's bonded to it. What? 69, exactly. So we know that when we're looking at it, it's a negative, so this is a CH2, right? So that means what? It's probably on the end, isn't it? It's on the end. Okay, something else we have to look at is that we have 3 carbon environments, but we have 4 carbons. So now we gotta figure that out too. Not gonna make it any easier, are we? Okay, so how in the world are we gonna do that? Well, we've got this piece of information, okay? Now, we have a CH2 that we've done. Now, how can we get a CH and CH3s in there and have 4 carbon environments? Would that do it? Having 2 of these be equivalent, bonded to a CH? You want to kind of see the reasoning and thinking? I'm not sure. Let's see if I'm right. Should have looked at this, huh? And that's exactly what it shows. Okay, you see how you can kind of just take these pieces and put them together? It's not always that easy, but we'll do it for now. Usually, and some of the ones you do will take quite a bit of time to do, so just plan ahead.
Dr. Henry, how did you know that the OH was attached to the 69.5?
Because of where it was. When you look at it, what they were doing with it, the 69.5 is a negative, so it has to be a CH2. And the 69.5 means it's next to an electronegative atom or an oxygen.
Okay.
That's, yeah, when you're going through those things, you know, that I said you have to have the general whatever on it. That's when you kind of need to know the electronegative ones, and then the alkenes, alkynes, and nitriles are over here, and carbonyls over here. So that's how I did it. So
Okay.
that's why those things are useful, beneficial on it. Good question. Thanks for asking that one. Yeah.
What if you have a charge on the DIP 135 that you don't have any negatives? How do you know where the oxygen is?
Well, again, if there were no negatives, you would have to just look at anything that's over in that region for the electronegative ones around the 70s or so. That would be that carbon, unless there's something else there that would do it. But generally, oxygens, it's the more electronegative of, well, fluorine would be more, but it's more electronegative than, let's say, chlorine and nitrogen, and so that would tend to be the one that would be shifted the most towards that. Some of the other ones, like, they're not going to move it that much, and you can get kind of confused as far as what it is. But. Okay, propose a structure for an aromatic hydrocarbon C11H16 that has the following depth 13 spectral data. Okay, what's the first thing you're going to look for?
Degrees of unsaturation.
How many is there?
4.
2 times 11 is 22 plus 2 is 24, right? And we're gonna minus 16, which is 8, and divide it by 2 is 4. Everyone following along on that? Okay, so we have 4, and it says it's aromatic. It shouldn't have even had, anytime you see 4 degrees of unsaturation, think of aromatic. I mean, that's just kind of a typical thing. So we know from this one that we have an aromatic ring. Get this off. So at this point, okay, where'd the brown marker go? Anyone see it?
It's right there.
There it is. I was looking for it laying down. Okay, so we can start off with this one, and we know that we have an aromatic ring. I mean, for one thing, it just tells us it's an aromatic ring. Let me do this a little differently. I will not be lazy. Okay, I'll actually put those marks in. Okay, so now we have an aromatic ring. Well, that's going to take care of how many of our proton environments. A lot of times you would start thinking, well, I wonder if it's monosubstituted. I mean, that would be something you'd think about. It isn't necessarily, but that's something you might think about. And so when we're looking at this, what is it that we want to look at here? Well, how many peaks do we have there in the aromatic region? They would be CHs or a quaternary, right? We can't have CH2s bonded to an aromatic ring. Everyone following that? Okay, so now we look at it, and first off, when we're looking at this, the 29.5 is going to be what? CH3, right? Okay, the 31.8, what's that gonna be? Is that anywhere there? So it's gonna be a quaternary. The 50.2 is going to be a CH2. The 125, 127.5, and 130.3, they're all gonna be CHs. Is there a 139.8? So that means that we have what? How can we have that? Well, if these are the same, these are the same in this, that would give us 3 carbon environments on our aromatic ring. Okay? So chances are, these are all hydrogens. And this is something that's on there. Okay? So now we have a 30, what was it? One of those, 31.8. So we have, of everything else, we're going to have 1 CH, right? We're going to have 1 CH2, and we're going to have 1 CH3. So now work on it. By the way, this is probably the 50.2, CH2. Because it's the only thing that would make sense since it's all hydrocarbons. When we're looking at this, we can take this off if you want. We have 6 carbons here, 7, 8, 9. So what's that mean? Yeah. So we have 1 CH it might have. There's several on there. Anyone got anything? Let's look and see what we got. We could spend forever on this, okay? So we've done all of this. And so the CH2, like we said, would be here. And we know that because it's the only one that would make sense with its being more de-shielded. And then we just simply have a quaternary named, that's what I messed you up on, a quaternary with 3 CH3s on it. And that is just being a C, not a CH, when I was saying quaternary, put it with a CH, so I was wrong in doing that. We said it was a quaternary and then I put an H on it, so, anyway.
I thought we said we only had one CH3.
Yeah, but that's all, the same environment.
So we're counting the environment,
Mhm,
not
because
just
the-
amount of.
The peaks tell us how many environments, it doesn't tell us how many carbons. Yeah, the peaks only tell us how many environments, so we can have 3 of them. This is just telling us the different environments that we have.
Okay.
We can have any number.
So if there was a 2 CH3, there'd just be 2 different CH3 environments.
Mhm.
So one could
Exactly.
be connected like a OH group and another one like that there.
Exactly.
Okay.
Okay, yeah, that's how that works. Okay, so C13 NMR helps us determine molecular structures, as you can tell. Still can't believe I forgot to erase that hydrogen on that, but anyway, sorry about that. It provides a count of non-equivalent carbons, as we know, so in other words, and we should put environments by that. And it gives us a lot of information, okay? So we can use it to get the electronic environment and the number of attached protons. So there's a lot of information on that. So when you're doing your labs, you're going to be sitting over there and you're going to have reactions, and you gotta figure out whether or not the product you get is what you expect it is, okay? And this is a great way of figuring it out. So here we have a strong base, and we're forming an alkene. What kind of reaction is that? Anyone remember? I'm hearing it. E2, okay. So do we expect this to be Markovnikov or Zaitsev or non-Zaitsev? Zaitsev, okay. It could actually be either. The main thing that matters on this is anti-periplanar, okay? But in this case, we can go either way with anti-periplanar. Either one can fall into anti-periplanar. It doesn't really matter since there's 2 hydrogens here and there's 3 here. We could make either of these, so then we're going to go to Zaitsev's, and so this is probably the one we would expect to happen, okay? All right, so did it. Here's our product, and so our NMR of our product, and what do we see? How many carbon environments would this one have? When you count them, put your number of fingers up here. Everyone's getting 5. You'd have 1, 2, a lot of times people forget that one. 3, 4, 5 with that, wouldn't we? And how many would we have with this one? Seven, right? There'd be 7. So now how many environments do we have down here? 7. So, and this would actually make sense. We have our alkenes right here, these 2 carbons here, and these are all more shielded environments. So it would make sense. So when we're looking at this, we can just see it and figure out that just on the number of SP3 residences, it does this. I do it with total number of peaks because they vary, they're different, but they're just looking at the SP3 ones and the kind of, and we see that it is indeed that one. And it did follow Zaitse's rule, and this is what it looks like. So it is 1-methyl cyclohexane, okay? Everything from, just kind of counting the peaks. We can look at all that. I would skip the summary. You can read through it. How many kinds of carbons and how many electronically non-equivalent kinds of carbons are present in the following compounds? Well, what's that look like? It's a cyclohexane ring, isn't it, with 2 methyl groups on it? Is that right? On adjacent carbons? Well, that gives us some information, but let's think about this. I'm gonna make a model kit, is that okay? I think the model kit on this one's going to explain it a little bit better, or make it a little bit easier to see, at least for me. So let's go ahead and just get there. 6 carbons on here. Yeah. Okay. So we have 6, and now we got to put two more on them. So it's got 1 going up. Just trying to get it the way it's shown so it won't be so confusing. So that one's going up. And this one is going out. So we have 1 axial and 1 equatorial. I'm looking at that correctly? Okay, that one's got stuff in it. Okay, so this is what it looks like. So how many kinds of carbon environments are there? Well, we do have kind of a plane of symmetry there, don't we? We have a plane of symmetry that's kind of going back and forth on it. So when we're doing this, we can see our plane of symmetry there. So how many did you think we have? 4. Okay, so you're right, we have 4 non-equivalent carbon environments, okay? So we got 1, 2, 3, 4, here's our plane of symmetry. Good job. Okay, the next thing though is how many proton environments are there? Well, I'm not gonna really ask you to count them, but what we're gonna have to see is that when we're looking at this, these 2 are gonna be different, aren't they? And these 2 will be different, okay? And so when we're looking at it, we actually have something that, there's the C13 estimation. And as you can see, we have our 4, ChemDraw agrees with you. And here is what the the good thing about carbons is that you can, just focus on carbons. It's not like you've got all this other stuff. So they're a good place to start for simplicity. And then from there, take it from there to your proton NMR and figure that out. But you can see here, 1.44, 0.088, 1.63. These are the same, but there's 2 different environments there. So we've got 1, 2, 3, 4, 5, 6 different proton environments. Okay. Any questions on that? And it's because we have these these are gonna be looking at these differently, and so they will be different. This one will see it as cis, this one will see it more as trans. Or this one, this versus this one, they'll be seeing it differently. All right, so that finishes that out. And I wanna go now back over here. Will they ever leave me alone? Okay, I just have to get it updated. And we've been talking about magnetic resonance imaging, MRI, and it does work on the same principles. There is a little bit difference as far as they go, though. Let's see if I can get this bigger print. Okay. So we know that NMR is very powerful for us, and we know how it's done because you've now done it, right? Or some of you haven't, but you will be doing it. And we take a small amount of sample and we dissolve it in a deuterated solvent and we put it through a tube. So now, how can we do that with a person? That's the question. And we spin it very fast so that everything kind of goes together and there's not these differences, etc. And so instead we've got this huge person that we want to be able to do an MR on. And that's what MRI does, really. Now, it's, as you know, it's got a lot of use. So what it does is it typically looks at hydrogen. Again, as we talked about in our pre-lab, which some of you, I guess everyone's had that. As far as the size of the magnet, it's a smaller magnet. It's not one like the huge ones or something that we don't put bodies in that. But it pretty much looks at hydrogen. Now they're starting to look at phosphorus and some other things, but hydrogen's gonna be there and they're looking for different environments in the body as far as hydrogen's gone. That's the main one at this point. And so from that, they can look at the density of the hydrogen atom and make a 3D type picture out of it. They can do all kinds of things as far as they can look at blood leaving the heart in a single stroke and soft tissue. And so it's really good as far as allowing the identification of the different types of tissue and what's going on. Again, they're looking at some other ones. There is a difference, though, when we're looking at it. And unlike in the NMR, the MRI used data manipulation techniques, okay, to be able to look at the 3D dimensions of the location of the magnetic nuclei, rather than the chemical nature of it. All right, so this is just an example of what it looks like. That looks awful. I think it looks awful. Okay, I want to go back now, and I just want to talk about something. Is it okay if I digress on my own interest at this point with you guys?
Absolutely.
All right. I'm going to digress. You don't have to worry about it. Don't take notes, okay? Unless you just find it interesting and you want to. Did I talk about this yet with you guys? Okay. Dr. Raymond Damadian, he was actually the inventor of the MRI. And when you're looking at this, would you think that he's got a lot of good qualifications? I mean, he's well qualified, isn't he? Well, he had this idea. He was working on some research, and he reasoned that the hydrogen and water might actually be responsive to NMR within cells. And so they got some cells and they checked it out, and they found that that was true. And then some other people that were around there that were doing things, they were looking at tumors, tumors that were out of the body, and doing MRIs on that. And they found that the tumors, the cancerous tumors, responded differently than the healthy tissue. So he's saying over here going, and he says, I gotta try this on a live human. I mean, that would be a great way to find tumors in people earlier and stuff. So he applied, and he started telling people, he applied for grants and started telling people. They all laughed at him, said absolutely no way can this happen. You'd have to spin the patient 10,000 RPM. In other words, they'd all be mush before it was all said and done, and the tumor would give them more life than the NMR would, or, you know, it's pretty much what it came down to. But he had an idea, and Damadian, by the way, was a very strong, or is a very strong Christian. I haven't heard that he's passed away yet. And he's getting up there, but he's still kicking as far as I heard. I haven't kept up with it much, but in fact, he's a Baptist, and he had people around him, and he wanted to find something to help them. I mean, he was very compassionate to a lot of people. But the experts laughed at him. The NIH wouldn't even give him a grant, so he had to come up and figure out some, and you know, just really beg for money to even be able to try to do this. Can you imagine that? This is MRI. We use it all the time now. He's trying to develop this out, and he can't get the money for it. The NIH said, hey, forget it, it's not gonna work. So he finally managed to get enough funds together, and he put in a patent for this, and this is his first patent, his original patent that he drew out, and it was in 1972. That's not that long ago, is it? When you really think about it, it's not that long ago. And this is what he said, and you can see a person in this coil and everything. So he proceeded to build this thing, and he was going to test it, and he was going to test it on himself, because who else was going to want to get in there and test it? I'm sure he might have tried a few animals in the process. I don't know. It doesn't say he did. And so he had doctors around and the paddles around just in case something happened he wasn't expecting and all this other stuff. And he put it on him, and he said, I'm going to get the first MRI, and I'm going to, you know. And he was excited. Everyone was excited, and nothing. He goes, oh no. So back to the drawing board, he started thinking about it, and he said, you know, the problem is I'm just too fat. I mean, that's what the problem was. And he's not that big of a guy. But he had built it too small, and the original antenna was only 14 inches in diameter, and he could barely, I mean, they had to just squeeze him in it. Again, he had the cardiologist, emergency shock paddles in hand, just in case, etc. And so they figured that the problem was he was too fat. Well, this poor research student he had, a graduate research student, was thin, real thin. And he kept trying, and eventually he talked him into it, okay? And so here it is. It took some convincing, but Larry Minkoff, he's the one he was real skinny, and he finally got him to agree to it. And they got the first MRI. It was on July 3rd, 1977. And there he is. They're recreating it at this point. But anyway, it's just showing what it looked like and why it worked on him. He was thin enough to be able to do it. Okay? Now the interesting part of this is that, like I said, Damadian is a strong Christian, and this is just showing an MRI. And he has this quote here, and I like this quote. It's I can't fathom just not believing in God creating our world. I just can't believe that. I mean, I can't fathom people not doing that. The non-biblical account would have us believe that all life originated from a single common ancestor, a slime mold, and give or take 1 billion years, we're expected to believe that the descendants of this slime mold climbed out of the ocean and stood up and started giving lectures. Do the math on it. The sheer statistics of that violate any sense of reality. So what's interesting is a few years back, a Nobel Prize was given for MRI. Anyone remember that? Probably not. You were too little. Wasn't that long ago, really. And they waited a while, because they always do on Nobel Prizes. And he wasn't listed. He did not get the Nobel Prize. They broke their own rules on the Nobel Prize. The Nobel Prize says that you have to do something that is original, totally original, and this was totally original. The ones that got it were the ones that put the math programs together to make it so you could see the differentiation of the Not saying they shouldn't have got it, although according to rules they shouldn't have, but, you know, they did a good thing. And he was outraged, and a lot of other people were outraged. He took a whole ad out, and I think in the New York Times, talking about fraud and all this other stuff. And I can't blame him, I really can't, you know, I mean, here he put his whole career and his reputation on the line. The other ones just took what he did and improved upon it. And a lot of people think it's because he is an outspoken Christian that he didn't get it. That's about the only thing that they really come up with, thinking is the reason that didn't happen. No one can say for sure, but it is kind of weird that they wouldn't give it to him. I could see giving it to all three to share, but why he didn't get it is just kind of, it shouldn't have been that way. Let's just put it that way. Anyway, there's articles written on it and everything. I just thought you might like a little bit of background information on the MRI. At least find it interesting. Oh, I forgot this one, I'm sorry. One more quote from him. He says emphatically that his greatest scientific discovery was to find that the highest purpose a man can find for his life is to serve the will of God. So yes, there are still Christian scientists out there that are doing great things for the glory of God. Okay? And no, we're still gonna, if I work on this morning, we're gonna at least get through a couple of slides, okay? Got it all ready for the widescreen and everything. Well, I'm gonna give out how, maybe we aren't gonna work on it this morning, today. Let me give this out instead. You can probably use a little practice. How many of you worked on the last one I gave you? You want to check your answers on it? Give you an idea of how you should be approaching these. We have any extras here?
Also an issue is your please address.
Oh, I don't need a blank sheet. Sorry about that. Why? I bet that was the one that, I actually probably do know why. We had the computer mess up. That was probably the one I messed up on. Okay, here it is. When we're looking at the first one, what is it that you need to do on something like this? Now, I'm going to mention this because you're going to have problems like this on your lab midterm and final, okay? So do I have your attention now? All right. So when we're looking at this and we're talking about this, what would you have to write on it? There's going to be, I think there's only one, there might be two on it, but anyway, there used to be three. Anyway, I don't know how many are on it right now. Haven't really gone and gotten it ready yet for one. But there's going to be a bunch to choose from, and then you have to figure out what it is. But if you get it's worth 10 points. Now, do I really have your attention? Okay, 10 points. So the question is that, and you're not going to get just this, okay? You're not going to get just the NMR. You're going to get the IR and the mass spec as well, okay? So it's worth 10 points, but getting the answer right only gives you 2 points. So that means there has to be something else you do than just count carbons, okay? So you have to be able to fully and totally analyze it out. I'm gonna turn this slide off, I think. Might be making it a little hard to see. Is that gonna be any better? Is that any better? That's worse, isn't it? Okay, let's see. Okay, I guess we're stuck with that. That shadow on it. Oh. From the screen. All right, so here we have it, and these are the possibilities. So when we're looking at this, what you would do is that you'd have to know, just not say, oh, well, I can see that there are, and over here are the carbon environments, 1, 2, 3, 4, 5, 6, 7 carbon environments. So which of these has 7 carbon environments? And when we do that, we see A is the only one with 7 carbon environments. That would get you 2 points, okay, out of 10. Now, obviously, there would be an IR that would show an alcohol, so that would help, and you could say that it had an OH of an alcohol in it, and it would also show that there was some CH2 and CH3 carbon hydrogen stretching. But we're talking NMR now. The other thing you'd have to note is that there's aromatic ring here that's shown. These are all in the aromatic region. Okay, so we're showing these are aromatic. So we have 6 that are in the aromatic, so that would say that all 6 carbon environments in an aromatic ring would be different from each other. This one's way out there, so it's probably the one with an OH on it. This, what's this right here?
The solvent.
Solvent. It's the solvent peak, so we don't want that. It's not listed over here, so it's not one. And then we have CH3 over here, okay? So we'd recognize these as our aromatic. This with the aromatic carbon with the oxygen on, the OH on it. This is our methyl group here. We wouldn't worry about which was which besides that. Then we get down here with the proton NMR. We see we have aromatic environment, electronegativity environment, and then a CH3 here as well. Give an approximate ratio of 4 to 1 to 3, integration ratio, and then also identify these as well. Okay, so that's what I'm looking for you to do. Determine how many carbon or proton environments on both of them. Identify what goes with what. I mean, now you can lump your aromatics together if you want to. And remember, in carbon we get general idea of what we're dealing with, so aromatic, next to electronegative atom, et cetera, how many carbon environments on the proton. I expect you to be able to look at number, the general regions that we're looking at form, how many proton environments, the integration, and the split patterns, okay? So when you're going through and doing that, look at those things, and we've run out of time.